Hello, I'm Dave Tabb, and today I would like to walk you through your first search using ProSight 4.2 in Proteome Discoverer 3. This is a very widely used software framework that we use for identifying top-down proteoforms for data-dependent proteomics of intact, undigested proteoforms. I am currently located in Julia Chameau-Rooc's team up at Institut Pasteur, where I've had a lot of interesting experiences working with protein identification. And I really felt it important that I take a look at this most widely used framework for identification. So we'll be starting with a raw file. I'm using one drawn from our own file servers. If you'd like to follow along at home, I'm not sure this one is actually publicly available, but there is a very related experiment at PXD 019247 that was previously published by this group. So feel free to work with one of the raw files from that collection using exactly the same processing, and everything should go just fine. I would note that in this case, the experiment I'm working with was run on a Fusion, whereas these were run on a Fusion Lumos. As a result, the experiments in PXD have a higher sensitivity than what you'll see in the experiment I'm running. Okay, so I have my raw file, that's wonderful, but I next need to figure out what search space I'm going to configure for it. And for this, I need a sequence database. Now, this is E. coli K12, and in this case, I want to grab a UniProt reference proteome that represents all of the proteins possible for E. coli K12. So let's pop over to the UniProt website. When you first go to the UniProt website, you might be inclined to just type E. coli into the search blank and off you go, but I want to tell you that that's actually kind of a rough habit to get past, because we want to search for not just individual proteins of E. coli, but rather the whole proteome. So for this, I'm going to start by limiting my taxonomy to E. coli. You can see that this is now changed to Find Your Taxon. I click Search, and I come up with 49 results. Why would we have 49 different species out there corresponding to this? Well, because there's a load of different strains, and there are even bacteriophages, viruses, that infect these critters that we also study. So let's now limit to bacteria, not the viruses, and we see that our list has gotten a lot shorter. Now we see Escherichia coli, E0137, E. coli, etc. So let us specify that we want 562 here. I would note that even at this level, there's a huge number of proteomes available for E. coli. I want to specify that we want strain K12 because that's the one that we shot through the instrument. So when we click on that and view proteomes, we still see there's 41 different proteomes available for just K12, but only one of them has been marked as the reference proteome. That's the one we want. So we're going to click on that, and straight away we see that it corresponds to UP00000625, and it has 4,448 proteins in it, and we can see that the BUSCO score on it is really, really high, that almost the entire bar here is covered up with this light green area. That means that single proteins that should be present in single copies are in fact present just once in this database. So that's lovely. Let's go ahead to click on UP625, and now we would like to see the proteins that appear in it. Oh, I've missed the link here. Here it is, protein count. I click on that. Okay, so I now have my long list of all the proteins that appear in UniProt knowledge base that are part of the reference proteome for Escherichia coli strain K12. I'm going to click on the download button. Now, ordinarily, if I were doing a shotgun database search with digested peptides, I would probably download a FASTA database of canonical sequences, or if I were working in a eukaryote, I'd probably grab the isoforms as well. In this case, however, I'm using ProSight Proteome Discoverer, and ProSight Proteome Discoverer really prefers that you start with an XML database. Now, an XML database allows the source of sequences to come with a whole bunch of post-translational modifications that are already known for these proteoforms. So we want to capture that information. A FASTA tends to be naked sequences with just free language descriptions, whereas the UniProt knowledge base XML comes with information about things like signal peptides, cleavage sites, and of course, post-translational modifications. I'm going to go ahead and download this compressed because that's really a sensible option with something like XML. It gets a lot smaller if you download it in a compressed format. So let's download that. And we see that down here in the bottom left corner, we're now downloading the file, and it's up over 4 megabytes, up above 7 megabytes. We're going to get there in no time flat. I'm going to open my downloads directory, and we will pop over to take a look at what it's downloading. And I believe that it has now finished. Yes, down there it did. Great, and we see that we have a 10.6 megabyte file. I'm going to unzip this file, though. You can see that it's called an xml.gz. That gz means it's been gzipped. So I need to extract this file from that format. Now, one of the awkward things about Windows decompression is that it doesn't support the gzip format. For that, I'm going to use some software called 7-zip. 7-zip is very, very good at handling a huge variety of different compression types. So if I want to grab that folder, I need to navigate to it. And it's in my downloads, which is always in this awkward spot to find, but okay, it's in C, users, D tab, downloads. I believe that's the correct place. Good. Okay, now our file name that we want to find is UniProt compressed true download, true format, blah, 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 blah. So something starting with U, in other words. So let's sort on name. I've got a pile of different stuff that I've downloaded over time. We're going to pop over to the UniProt here. So we have a file that was downloaded today, November 25th. That's the one we want. And I'm simply going to click extract on it now that I've got it. And it has no problem recognizing the compression format. Now when I pop back to downloads, I see that I have a directory with the name of the UniProt XML, and that's our file. So I'm going to grab this one and move it to the location where I have my raw file. I'm all done with 7-zip. Nothing else needs to be zipped or unzipped. I pop over to the demo directory and copy this in here. So now I have a raw file from the Thermo instrument, and I should momentarily, as soon as Windows lets go of the file, move that into the directory alongside this. Now, it's worth noting that in ProSight Proteome Discoverer, the process of setting the post-translational modifications and the sequence database come together, and they are separate from the search. I'm really very unsure why the system is being so troublesome about simply copying a file from one place to another. I'm simply going to call this a Microsoft thing and ignore it. So now we see that the file has in fact joined this other one in the file. That's great. So let's now launch Proteome Discoverer. I've done it already. You should note that Proteome Discoverer takes several seconds to launch. So if you double click the file and the user interface doesn't pop up right away, that's not an indication that anything is wrong. It's just that the software takes a long time to load. So I've pre-opened the file, and I want to note that I need to create a search database in the database manager. That's what this little feature right here is. So look for the kind of cylinder that has a gear beside it. That's the settings for databases. We're going to open that up. Now we see that I have a variety of directories that I've already created from past databases. If yours is a fresh installation, none of these bottom things will show up. But here we're going to simply create a ProSight PD database. And the software naturally wants to know, what are we starting from? So I need to provide the file path. Now I could type it all, but I'm lazier than that. So I'm going to click the Browse button, and now I need to specify that I want to go to my ProSight PD demo directory and grab this particular XML that I've created. There it is. And you'll note that it sees it right away. Now, I want to note something kind of odd here. If I'm using a FASTA file as my starting point rather than a UniProt knowledge base XML, I would need to come down here and specify that I want the FASTA rather than the XML. So just be aware that that's the case. So I'm going to grab this UniProt XML file and say open. It will take a moment to sniff over the file and make sure it's fine. And I want to note something a little bit odd about this that I haven't really got a satisfactory explanation for. I have 4,448 results in my UniProt knowledge base for this reference proteome. But that same file, when imported into ProSight PD, shows 4,051 UniProt formatted proteins. Now, why is that? I'm not really sure, and there could be a variety of reasons that lie behind it. But at the moment, let's just say don't expect the number of entries in your database to match exactly with what with what ProSight PD will see from it. Now, there's a very important thing that we need to do. I already said that the UniProt XML file contains definitions of post-translational modifications, but there are some modifications that we surely expect that are not annotated in the UniProt file, and for that we can deal with the ProSight annotator. When I click on the ProSight annotator, I get the ability to view individual proteins. You can see that I can click around here, and if I click on a very well-documented protein, I might find that some of them have particular PTMs that are already associated with them. But frankly, the number of PTMs is not huge in this collection. So as I look at individual proteins, I can see that some of them, here's a fine example. So this protein is 6-phosphogluconate dehydrogenase. We see that there's a large number of proteoforms that derive from it, and that's because it has these different sites that have been annotated with different PTMs. If I click here, I see that this threonine has a phosphorylation possibility. If I click on the serine, I see that it has some modifications associated with it. So that's lovely. So why am I saying that there are some PTMs that aren't here? Well, it could be that I have specialist knowledge because I've been working for a long time on a particular protein of E. coli, that I can come in here and make absolutely certain that that modification is listed or add it if it isn't. But in fact, what I'm saying is that the chemical processing of our samples leads to oxidation. As a result, every time I see a methionine in this database, I need to consider it both in its ordinary mass and in its oxidized mass, which is 16 mass units higher. So I could do that for each and every one of these protein entries, but going through 4,000 of them would be a serious bummer. So let's instead look at this Modify Available PTMs button under Point Features. As I click on that, I see that I have a large number of included features where trimethylation, for example, has been annotated at 3 locations throughout the entire database. Monomethylation has been annotated 28 times, and so on. But we also see that there's a very large potential number to the side, which is to say that if we were to allow for all sites that could potentially carry trimethylation, we would instead be annotating 152,000 sites in this database. We don't want to do that at the moment, but we do want to allow for every possible methionine to be allowed to carry an oxidation. Now, I don't want to allow for just any kind of oxidation. I specifically want methionine oxidations. So I click on that plus to expand it out, and now I see that methionine sulfoxide is an option. So just methionines will be allowed to be oxidized. So I'm going to grab this global button to force all methionines to be considered in both oxidized and non-oxidized form. I then need to click the Save button down here. And when we pop back out to this interface, suddenly we see that anytime a methionine appears in our protein sequences, it's now highlighted, and that's to say that this is now allowed to oxidize. So that's lovely, that's everything we want. I'm not going to add any other modifications at this point, although we could consider things like disulfides or say the when glutamine is at the N-terminus of a protein, we could allow for it to lose ammonia. We could do sorts of things like that. But at the moment, we're just going to focus on adding methionine oxidation. So I click the Save button to put that into effect. Now we need to have a name that we use with this database, and that name should be really specific because the name is going to be something that is going to have to clue me in months to come that this database is part of this database manager on this computer, and I might want to come back to it at some later date and add another modification on top of what I've already got. Because I might do lots of searches against the UniProt proteome, but they may differ in which modifications they consider, right? So I'm going to call that today's date, 2022, 11/25, and I'm going to just call it E. coli K12 XML. All right, I'm going to copy that and put it in the description as well, and then I can click Create Database. This process doesn't take a huge amount of time to run, which is lovely. Now I see that I have my E. coli K12 XML stored in the file, so that's lovely. I can now close the ProSight PD database manager. I can always reopen it right here. And now I want to start a search of my particular raw file. So for this, I'm going to click on the New Study button up here at the upper left. I need to give it a name, I need to specify where it's starting from, and so on. So I've already created a directory that's going to contain my demo. It's right here. So I'm going to copy that path and save that as my root directory. Well, if it would let me type there, that would be lovely. But instead, I'm going to have to navigate to it by copying it there, and then click Select Folder. Great, now that's in place. I need a study name, and for this, I'm going to use the name of my data again, 2022-11-25 E. coli K12 demo, let's say. Okay. Now, I don't need to import a result from any prior file, but I do need to set up a processing and a consensus workflow. Think of processing as the means by which we're going to generate identifications, and consensus as the steps by which we will refine those identifications to determine which ones we actually trust. So for this, we need to specify our processing workflow. These come with a huge number of workflows. Once you've got ProSight PD installed, you should find down at the bottom these list of potential searches. If you're really interested in saving lots of time, you might use something like the Discovery Proteomics search, but I really feel it's quite important that you consider the possibility that the protein sequences have been truncated in important ways. As a result, I almost always use the ProSight Proteome Discoverer truncation search, and I wanted to compute false discovery rates for me. So for this, I'm going to choose the PSPD truncation search with FDR. This is my go-to. It's very rare that I attempt to use any of the other search modes within this software. From here, I need to choose a consensus workflow. And in this case, the data I have high quality precursors and high mass accuracy fragment ions as well. So this is high data. In this case, I'm going to do some degree of label-free quantitation as well. So let's go ahead and click on this, and then I'm going to say OK. The software takes just a moment to initialize the new study. It's creating a directory off of the root directory that I set up in order to store the evolving workflow that's being assembled for it. Okay, so now we're at the study definition page. Our study is a really simple one. It's going to use just a single raw file and a single database. There's no cohort A versus cohort B kind of thing going on. But I do need to tell the software which raw file it's going to use. So I need to click Add Files. Now I note that this software is a little tricksy. You can see that it's jumped back into the last place I tried to launch a search from. In this case, I need to specify I actually want to use the root directory that I told it to use, the PSPD demo directory. Here's my raw file. I click it and say OK. That's quite lovely. Now I should have a raw file listed under input files. It's not enough to have it listed in the input files, though. I need it to be included in the processing step. You see that it says files for analysis equals 0? That's obviously not acceptable. I've just listed a file. Obviously, I wanted to process it. So now grab this file and drag it over to the files for analysis. I'm sure that's a very sensible workflow for somebody. All right, and now we want to put a name on our analysis. I tend to use a different name than the raw file I'm working with, typically because I'm trying to use, I'm typically doing a search that involves multiple files. So I'm going to use my study name all over again, and I'm going to paste that in here at the top. Okay, great. It's not good. Oh, I have to copy it in here. I'm sorry, my bad. I copy it in there, and now my result file and my result file for consensus are both given this new name. So that's exactly what I want. Okay, now the part of Proteome Discoverer that most people, I think, visualize in their talks and so on would be the workflows. And I want to emphasize that although we're doing IDs, that's not treated as one workflow, but two distinct workflows, a processing step and a consensus step. You see that those are separate workflows. I wanted to note as well that the names of these processing nodes are not necessarily completely intuitive for everyone. I think many people at this point are aware that when we do an identification for top-down proteoforms, one of the things that we must do is deconvolution. Deconvolution is handled here in crawler. The crawler, a high crawler, is the specific deconvolution node intended for use with high-resolution, high-mass accuracy precursors and high-resolution, high-mass accuracy fragments. That's one we want to use. But behind the scenes, what's actually happening is that crawler is calling extract. Extract is the deconvolution software that we also find over in software like Freestyle. So we can see that if we wanted to change how it was operating, we could change those parameters here. I would particularly note this feature, highest charge. If you are working on a very large proteoform and have set up your instrument to capture lots and lots of spectra from precursors that are charged, say, 40 and 50 plus, then doing a highest charge of 30 doesn't make any sense when you're trying to analyze the data. For that, you would definitely need to open up the ceiling on that. There are a lot of features here, and I wanted to note that this is not the complete list. If you're really interested in controlling how these things function very closely, you would need to do show advanced parameters, and suddenly we have a much longer list of options to play. Okay, let's now look at the last of these processing nodes. I note that it's marked with this big exclamation mark. That's to say you have to do something here before you can actually execute this processing pipeline. So I click on this option, and I note that the input database has not been set. Yes, I just added it to the database manager, but I haven't told the search that it must use that database. So let's now click on the field for input database, and I see that in a new feature that they've added with Proteome Discoverer with ProSight 4.2, they've added the ability to actually enumerate the databases in your database manager by just doing that click. So in this case, I want to specify that I'm doing the E. coli K12 XML database that I set up initially. As soon as I select that option, I note that my exclamation point on the subsequence search is gone. And that's because I've already satisfied all of the requirements, all of the fields I must provide in order for this search to take place. Now, I've already said that all PTMs to be considered must be enumerated in the database within the database manager. So they're not set at search time, they're set at the time you put them in the database manager. But there's a little bit of a lie built into what I said there. And I wanted to note that in ProSight PD, as in other tools, the N-terminal acetylation is frequently treated as a special case. You don't have to specify N-terminal acetylations in Database Manager. Instead, that's usually set up here under the N-terminal modification field. You can see that you can also consider things like pyroglutamation and formylation there, but we're not going to alter those at the moment. We're just going to allow for the possibility of acetylation. This does not require proteoforms to be acetylated, it allows them to be. And also, I have things like how many PTMs am I allowed on an individual proteoform? If you set this number up to 10, expect that it's going to take a very, very long time to run your search. Setting it above the default of 4 is generally not recommended unless you have good reason to expect, for example, that a protein is just hairy with phosphorylations. Okay, so now we have set up our processing step. All of these are configured appropriately, and I can come over to my consensus step. We see that we have a grouper going on here for grouping together spectra that match to exactly the same proteoforms. We have something that does a validation not just at the prism level, at the proteoform spectrum match level, but at the proteoform level itself, and even things to do some filtering at the level of accession. All of that is built in here. We're going to compute false discovery rates. That's part of the consensus step, and it's even going to do a filtering because the workflow that we chose is the 1% FDR one. So it's actually going to apply that 1% FDR threshold for us. There are also a couple of features here that can cause some searches to trip up a little bit. And I'm just going to mention that if you're not really invested in how strong an MS1 signal you have for a proteoform, then you don't actually need to have steps 5 and 6 on here. You can turn off the feature mapper and quantifier simply by clicking them and punching the delete button. So I'm not going to do that because I want to see if we get a warning message about that. Instead, I'm going to go ahead directly to save to run my search. You can see that it's colored in green here. That means all of the steps, all of the bits of information I'm required to provide have been provided. It is now okay to run. So let's click the run button. All right, so one of the things that we get is this odd error on grouping and quantification. We see that there are no ratios defined in the grouping and quantification tab. In some cases, you can see errors that suggest that if you're going to do a ratio between two files, that you actually need to specify which file is A and which file is B, and so on. And I wanted to note that at this point, I have the ability to simply click Ignore and go ahead. But instead, I'm going to just deal with this problem my own way. I'm going to click the Abort button and say, I don't actually care how intense a signal I have for my proteoforms. So I'm going to click the quantifier processing node or consensus node and delete it. I'm going to click on the feature mapper and delete that. Now, when I click Run, I should move straight ahead, starting analysis. Okay, so it takes a moment to get everything into place, which files are reprocessed. And now I note that the administration interface has popped up. So our study is still open back here. We can see how we configured it, but this is now it's actively in motion. So we can see the progress of this by looking at the administration tab. And the administration tab shows that right now we are running the processing step. Now that's not so informative all by itself. And I'm going to note that the great majority of the processing time for a job comes in the processing stage, not in consensus. In most of my searches, I find that processing is multiple minutes, while the consensus step, even for a study where I've got 4 or 5 raw files, is usually finished within a minute or two. So that's not going to have a huge impact on the overall runtime. Most of that is going to come in this first processing stage. So because we clicked out the plus beside the processing option, this little plus right here, it's now expanding out to show us how things are going in flight. And I wanted to note that the great majority of the time that these searches take for me come from deconvolution. So you see that crawling, C-rawling, or whatever they want to, however it should be properly pronounced, crawling is this process by which the software looks for spectra that are appropriate for search. In other words, tandem mass spectra. It's enumerating those, and each tandem mass spectrum, or each set of tandem mass spectra that are identical copies, are being deconvolved. And this deconvolution is taking place in extract because that's the way we configured it. So the crawler processing node calls out to extract for that processing to take place. In this case, because I'm using an experiment from one of our older instruments, we have relatively few spectra overall. I think it's something like 2,000 or 3,000 in the raw file rather than 10,000. As a result, the search is going to move along a lot more quickly. So what we see is that the software has batched up all of the spectra into 4 batches, and it's processing batch after batch. The first batch was about 428 spectra. We see that there are, that it's finished about 606 in the second batch, and now it's moving on to batch 3 and so on. So this, I have to say, these batch numbers are somewhat unreliable. This morning when I was running a search on here, it said at first that there were 56 batches, and so it said batch 1 of 56 and 2 of 56, and naturally when it got to 55 of 56 and 56 of 56, I was very excited thinking it's almost done, but it kept going until batch 64, so don't let it lie to you. The software may or may not finish when it has done 4 batches in this case. But we can see that even on my little laptop, it's a Ryzen 5 with 4 cores, we're still taking a fair bit of time just to handle the deconvolution step. We see that Spectrum Selector, though, is making very good progress. It's cranking through all of the tandem mass spectra in this particular raw file, and with that, it's done. We've already handled all of the deconvolution necessary for this experiment. Okay, so we had 1,492 spectra, and now we're going to process through that and do our search. So ProSight PD has been really well optimized over time. If we were to open up the task manager for my computer and click on performance, you would see that it's keeping the processor really busy. The software does a really good job, I think, of using your processing resources very sensibly and using that to get pretty high throughput. To be able to, in my mind, the criterion for how fast is software largely stems with how long it took you to collect the experiment. In this case, the instrument had, I believe, 90 minutes to collect all of these tandem mass spectra, and my laptop is going to handle all of that identification in less than 90 minutes. So I find that very comforting. We see that the memory usage is not terrible. If you have a laptop with 4 gigs of RAM or even 8 gigs of RAM, you may find that some of these searches will require more memory than your computer has at hand. So having 16 gigs of RAM should generally get you covered in most ProSight PD searches. If your computer has just 2 processor cores rather than 4 or 6, that can come as a bit of a hindrance, and certainly using ProSight PD on a computer with just 1 processing core is likely to be quite a source of frustration. But it is very good in my mind that the computer can take advantage, that the software can take advantage of multiple cores. This computer has a processor with 4 cores, as I said, but each core acts as though it has 2 threads. So it masquerades down here under logical processors as having 8 threads, even though there are only 4 cores, which is why it is keeping my computer so very busy. Hopefully the recording of this of the presentation still moves ahead just fine. Okay, so it may be just a moment before it finishes, so I may just stand quiet for a moment and even accelerate the video so that you don't have to wait as the computer chews and chews and chews on spectra. But at the very end, the consensus step should move ahead very quickly indeed. And with that, I will allow for some light music. All right, as you can see, the initial search required about 11 minutes, of which the search was about 7 minutes. So this is one of those occasions on which the search actually took more time than the deconvolution. You can see that that's up front here. So having finished the processing step, we've now moved on to the consensus. And that's not a hugely involved step. It's just something that requires that we do an evaluation of decoy hits among our proteoform spectrum matches. And then we need to apply a false discovery rate cutoff. That step doesn't take a huge amount of time, but we can see that some fraction of the spectra overall will end up passing this FDR filtering. There's not a whole lot to say on this, except that at the end you should see this nice green banner that says completed and OK, completed and OK. So the consensus step up top finished OK, and the processing step down below finished OK. I wanted to note as well that we submitted this search at 3:08 p.m. and it finished at 3:20 p.m. That means we spent a total of 12 minutes searching this raw file. And you might think to yourself, well, gosh, if that's all the time this takes, I'm really in a great shape. But keep in mind that not everyone is going to be searching E. coli with just 4,000 proteins. What if you're dealing with a human sample where you have tens of thousands of proteins in your sequence database? What if the number of PTMs you're considering is very large? And very importantly, what if the number of raw files is larger than one and has a very high MS acquisition rate? Those things would lead to a much longer search than a simple 12-minute process. But we can see that that process is now finished, completed, and it's time for us to now open the result file. So let's pop over to the directory that we were storing all this information in. You remember we started with a raw, we downloaded the XML. This directory is the one that we created to store our search results. So if we click into that, you should see some results like this pdResult file. A PD study is kind of the definition of how the search is to be run. The PD result is what came from it. Along the way, it also created an MSF file to store things like the deconvolved spectra that are subjected to search. So we now want to open this PD result in Proteome Discoverer. Okay, so I can simply use the File Open Result option. I click on that. Again, it's defaulted to the last time I opened a study rather than the directory I actually want. So I'm going to grab the path from here and force it there. And now I see the PD result file that came from it. I searched about a half gigabyte raw file and it's given me a 116 megabyte output. It takes a moment to open it. These are fairly complex databases, but there's a lot of good information here to work with. You can interrogate your data at a variety of different levels. Maybe you're interested in the spectra that were claimed to be identified. Maybe you're interested in the proteoform spectrum matches that resulted in particular. At a higher level, maybe you want to see proteoforms regardless of how many spectra were matched to them, or which isoforms, in the case of a eukaryote, for a given protein sequence were observed. But in this case, simply looking at the accessions gives us some indication. In this case, the protein that had the largest number of proteoforms was the DNA binding protein HNS. I believe in this case we're sorting on the basis of, no, it's not on the basis of Q value. Probably it's sorting on the number of prisms. So here we had 25 different spectra that matched to 10 different proteoforms for this one accession. That's why this ends up at the top, the number of spectra matched to it. Okay, but I tend to want to look at this on a spectrum by spectrum level to know specifically which proteoforms are matched to which spectra. And that's what this PRISMS table is really good for. Frequently, the software that we want to upload to say what were the identifications from our search are found in this PRISMS table. Now, it's obvious, I think, that uploading the Proteome Discoverer file itself is possible, and people with Proteome Discoverer can read it. But what about all those folks who don't have this installed on their computers? What if they have an older version of Proteome Discoverer installed and they don't have the latest 3.0 installed? In a case like that, the PD result file may not be of much use to them. So for this, I'm typically going to edit the fields that I output to a table. I'm going to click on this, and I'm going to note that the set of defaults in which fields appear seems pretty sensible, but there are a few things that kind of bother me. One is that when I'm using this output table in Excel, these two fields for external top-down displays tend to create really weird effects in Excel. It doesn't like having these really long strings that these fields contain. So I typically turn that off. Now, I want to note that when I did that, my external viewers vanished from this table as well. So if I wanted to open ProSight Lite automatically to visualize that prism, I can't simply click on that button now. That's affected by this external top-down displays. The next thing that I think is definitely a feature that should be turned on, is the fragmentation scans option. I'm going to open that up. Fragmentation scans is something that tells us exactly which tandem mass spectra from our raw file are associated with this particular proteoform. It seems like a very critical piece of information. I always want that turned on. And there's one other, sorted down here alphabetically, called original precursor charge. For me, it's very, very valuable to understand the distribution of precursor charge states that led to identifications. So for me, I'm always going to want to have that turned on as well. So when I look at the table, I can scroll all the way to the right, and now I can see that my fragmentation scans column is showing me exactly that this is scan 801 in that raw file, which is named over here, spectrum file, corresponds to the proteoform that appears over at the extreme left. Now, something that you may not anticipate, oh goodness, is, I guess I'm not going to be able to just scroll to see that, but on occasion, you will find that Proteome Discoverer, or that ProSight, has matched multiple fragmentation scans as though they're one thing. This doesn't happen a large fraction of the time. In my experiments, I think it happened with approximately a 2% occurrence. But there are some cases in which an individual proteoform spectrum match is actually made to a pair of spectra, not just one. The sensible way to go after this would be to sort on the fragmentation scans column. If any of those is a 2, that should appear up at the top, I think. So if I roll to the top, no, all of these are singletons. So in this case, the software is not identifying multiple spectra collectively. So that's helpful to know. Okay, but I added the original precursor charge. You can see that that appears right here. If I'm particularly interested in the large stuff, I might sort on original precursor charge to look at the largest proteoforms that I have identified. Those are likely to appear at some of these high precursor charges. So we see that although the software was allowing for a maximum precursor charge of 30, in this case, I was able to identify up to plus 25. So one of the obvious things that you would want to do is to be able to export this table. That's appearing up here in the File Export option. I can say, create a Microsoft Excel table or a tab delimited file from this current table. And all the columns that I told it to opt into will be included. But I want to note it's going to default to displaying protein information, not prisms, even if I've clicked on the prisms page. So I need to specify I want to output prisms and click the export button, and that will be created for me. So that's very helpful, but be aware that you actually have to specify you want to output the prisms table, because when you're exporting to Excel, you can export multiple pages as different tabs in your Excel spreadsheet. There's one last thing I want to point to before we leave, and that is this kind of innocuous looking document icon over at the right. Summary information is really, really valuable. Someday you will be very glad that at the time you made this search and exported text files from it, that you also exported this information. So I would strongly recommend that you copy all of this information, which includes the samples and files, the analysis settings, including runtime information down here at the bottom, the validation information, and the configuration, all of it. Copy all of that and paste it to a big text file. I usually create something with the same name as my pdResult file, but with the extension log. And that log is very helpful for me to remember how exactly I did this search. You don't just want to have a table of prisms all by itself and try to remember how you did that search many months later when you're writing your materials and methods section. Export the log as well, because that's going to tell you how you did it. By that time, you might have moved to a different version of Proteome Discoverer and discover that your pdResult file doesn't open. So by all means, copy the materials and methods that becomes available with this document button just to the left of the blue and green boxes. Okay, so I hope that's a useful overview of the software and that you have a better sense of what to expect as you run your first search. Remember that if you don't have access to this particular raw file, any of the ones from PXD 019247 should be able to help you with that. In there, you can click on the project FTP and download individual RAWs from that. So that should help you a lot if you want to replicate exactly this same search on your computer. Okay, with that said, thank you very much for watching this video, and keep your eyes open as more of these tutorials show up over time. Thank you so much.